Okay, so we're beginning the last topic of the semester. So we're going to move on to chapter 11, which is all about trees. And so, right, so the last few topics we're going to talk about are really just more topics in graph theory, but they're all about graphs which have a particular structure, and these graphs are trees. And so recall that a tree is just a graph with no circuits, right? Technically, you may want it to be an undirected graph with no circuits. We'll also see how you can add on directions as well. So I'm just going to put graph with no circuits. Right. So remember, maybe it looks something like this picture that I'm drawing now, where there are a few different paths which look kind of like leaves or branches, which is where the terminology comes from. Right. Right, and so for a lot of purposes, it helps if you distinguish a particular vertex as kind of like the starting point of the tree. And in this scenario, you call it a rooted tree. Right, so a rooted tree has some distinguished vertex, say V as the root or the starting point. And every edge is going to be viewed as being directed away from the root. Right, so in the picture I have that I've just drawn, well, if V is my root, I'm going to view all these edges as pointing away from V, right? So the tree kind of begins at V and goes, all the edges are viewed as going in the direction away from V. Uh, and so for most purposes, once you fix a root, and if you know what the root is from context, we can kind of ignore the directions on the graph because they're all pointing in the same direction, right? So once the root is understood, we'll typically not include the arrows in the drawing. Not reference or draw the directions because it's technically a directed graph, but the directions are all pointing. They can only point in one direction, which is going away from V. Great. Okay, and so there's just like with every new concept in this course, there's a lot of terminology associated with trees so that we can talk about them rigorously. So I just want to say a little bit about this. And so the terminology for trees, I mean, you can think of, for example, you can think of like an ancestry tree where you have like the root is some person and all the vertices below it are some descendants of that person. And this gives you a particular model of like of what's called an ancestry tree. And so a lot of the terminology, because of this, a lot of the terminology associated with trees is genealogical in nature. And if you want to think about where do trees come up in practice, I mean, we'll see some applications that are different later on, either today or in the next lecture. But a simple situation where they occur in practice is just modeling like an ancestor diagram, right? So let's say I just draw this sort of subsection of a tree. And let's say there's some root. So this is some directed tree where the directions are all pointing away from whatever the root is. Maybe W is the root, for example, here. I'm just going to list out some different ways of talking about the different vertices in this tree, right? So since U is somehow above V and T in this graph, we say that the vertex U is a parent of V and T. And similarly, we would say that V and T are children of U. Right. And so notice that, well, U or W is a parent of U, or U is a child of W. and V and T are children of U. And so we would say that the vertex W is an ancestor of V and T. And similarly, we would say that V and T are descendants of W. Right, so again, it's genealogical notation. Right, and so notice that, well, V and T are both share U as a parent, so we would, as you would expect, we also say that V and T are siblings. Right, and so whenever you hear this kind of terminology used in the context of a graph, it means exactly what you think it would mean, right? Just think of the graph as representing some kind of ancestor history, and that's what it means. Right, and then one more bit of notation that I want to talk about. So this is one scenario in which trees commonly a very common type of tree that occurs in practice. So a rooted tree is said to be M-ary, where M is some integer that's bigger than or equal to 2. If every vertex has fewer than but up to M descendants, or sorry, up to M children, right? So if every vertex V in the tree has less than or equal to M children. And so when the case, or if M is equal to 2, we don't call it a two-ary tree, we call it a binary tree. Right, because two-ary is kind of a weird phrase. Right, and so what's an example of for example, a three-ary tree, right? So notice that in the definition, I didn't say it has exactly 3 children. It could have fewer, but it just has no more than 3, right? So for example, maybe this is the root. Maybe it looks like something like this. Right, so this is an example of a three-ary tree, because if I look at any given vertex, how many children does it have? Well, it has no more than 3. Right. Okay, and so that's some basic terminology associated with trees. And what we're going to spend the majority of the rest of this lecture, and also a lot of our last lecture, talking about are things called spanning trees. And so what is a spanning tree? Well, let's suppose that we have G, which is a simple graph. And now G is just allowed to be any graph, not necessarily a tree. So a spanning tree of G is a subgraph of G, which is a tree in which contains every vertex, right? So we have some graph G, and the spanning tree will be some subgraph which looks like a tree, which is contained in G and hits every vertex. Right. So a subgraph which is a tree and contains every vertex of G. Right, and so one thing to point out, which we'll see a little bit in some examples soon, is that there may be more than one different way to find a spanning tree. Like there could be many different examples given a fixed graph of a spanning tree in the graph. Great, so let's look at a picture. So for example, let's suppose my graph G is this graph. Just give me a second to draw it. Right, so this is my graph G. Let's find a spanning tree, which I'll call T. Well, one example is if let's start at A and move to B, and then move from B to C, and then down to D. Remember, I want to hit every vertex, but I don't want to produce a circuit. So I don't want to I don't want to add an edge from A to D, so I'm just going to leave that alone. Right, well, C also connects to E. E connects to F. again, there's an edge between C and F in the original graph, but I don't want to include that here because that would produce a circuit. And so finally, let me end that with G, right? And you can see from the choices I made that this is not, again, there could be more than one spanning tree, right? Because instead of, for example, instead of adding the edge from F to G, I could have instead added an edge from E to G, and that would have given me another spanning tree, which is different, right? So there's in general many ways to find a spanning tree in a particular graph. Right, and so the problem we're going to be considering is, let's say you're given an arbitrary graph with maybe 100,000 vertices, which potentially has on the order of 100,000 squared edges in it. And so the problem is, given this graph, how can you find a spanning tree in the graph in an efficient way? And so we're going to discuss two different algorithms for solving this problem. One thing that I want to point out before that, though, is, well, why is this problem interesting, or what context does this problem arise in? Well, one example, which is mentioned in the book, is, well, maybe you can think of this graph G as modeling some kind of network, right? Each node can be some like data center or some a computer or something like that. And, well, why does it help to understand a spanning tree? Well, if you know a spanning tree, if you know a particular spanning tree in your network, it can make the transmission of data between different nodes more efficient. Right, because if you know a spanning tree, you can still send your data throughout the network to hit every single node, but there's no redundancy. Like, you're not going through the same node more than once to reach everything, right? So you just travel along you send the data along every edge exactly once, something like that. Right, so this is one scenario in which these things arise. We'll also see, I think, later on some problems which you can solve by finding some mathematical problems which you can solve by finding spanning trees. Right, so before we get into the algorithms about how to actually find these things, I just want to mention one mathematical property, which is one way to characterize connectedness of graphs using spanning trees. And so there's a theorem, which is the following. So suppose I have a simple graph G. The theorem is that this is connected, meaning the graph is in one piece somehow, if and only if you can find a spanning tree, if and only if G contains a spanning tree. Right, so spanning trees characterize whether or not a graph can be connected. Right, and so how does the proof of this work? Well, remember, here we have an if and only if statement. If and only if means that if I want to prove A if and only if B, I have to show that A implies B and also B implies A, right? If and only if means that the two statements are logically equivalent, meaning they're either both true or both false. And so in order to prove an if and only if statement, I have to show that the first statement implies the second, and then that the second statement implies the first. Right, and so one direction, I'll do the first direction. So let's suppose that G has a spanning tree, right? So I'm going to show that the second statement implies the first. Well, I want to show that this implies that G is connected. Well, it's actually not too hard to show this, because what do I need for G to be connected? Right, so let U and V be any vertices on G. Well, in order for G to be connected, I need to show that if I pick two arbitrary vertices, there's always a path between those two vertices. But if my spanning tree contains every vertex, in particular, it contains U and V, and so I can just follow the path along the tree from U to V. Right, and so that proves that G is connected. Right, and since T is a subgraph of G, any path in T is a path in the original graph, and therefore there's a path in the original graph from U to V. And since I picked U and V arbitrarily, it follows that G has to be connected. Right, so that's a relatively straightforward argument. And so the second part, well, I want to show now that if I have a connected graph, which is simple, right? So if G is connected, we can always find a spanning tree. Right, and so there's a way to argue this abstractly to prove that it always has to exist, which is written out in the book for you if you want to look at it. What I'm going to do is just skip that and move ahead to study two different algorithms, which give you a constructive way to solve this problem. Right? So it not only implies that there will always be a spanning tree, but we'll look at two different ways to actually find a spanning tree. Right, so we'll look at two different algorithms that accomplish this. Okay, and so the first algorithm is something called depth-first search. I forgot the T. Right, and so this is the first algorithm to find a spanning tree in a given graph. Right, and so what I'll do is first describe the basic idea of how this algorithm works and look at an example, and then we'll talk about how to write down how to program it using pseudocode, and then look at the complexity. Right, so what is the idea? Well, in the first step, what you do is just fix an arbitrary vertex in your graph, and you're going to treat that vertex as the root of your tree. Right, so V will be the root of the tree. And so in the second step, what you'll do is just travel along a path in the graph arbitrarily until you can't anymore without creating a circuit. Right. Oh, sorry. Right, remember we want to produce a tree, and so in order to produce a tree, whatever subgraph we construct can't have a circuit in it. And so what you do is you start with this vertex V, you keep adding edges until you can't add any edges anymore without returning to somewhere you already visited. Right, so you add edges until you can't without returning to a vertex that was already visited some step before. Okay, and so you may object here when I'm saying, okay, travel along an arbitrary path, right? So if we're talking theoretically, that works. Like we can all understand what this means, but how do you actually program like the computer to travel along an arbitrary path? We'll see later on that you can make this more rigorous when you program it, and you don't have to. You can ignore this issue. But just for informally describing how it works, hopefully this is sufficient. Right, and so right after step 2, eventually you're going to hit a point where you can't add any more edges. So there's one case in which you've hit everything, in which case you're done. The more interesting case, though, is well, what happens if you stop but you don't pass through every vertex when you're constructing this path? Well, this is where the third step comes in, and so what you'll do is you move back to the last vertex visited, which I'll call, say, W. All right, so this is after stopping. After part 2 stops, we're going to move back to the last vertex visited, say W. And then so this vertex W may have some edges leaving it, which you ignored the last time you passed through W. And if it does, well, you'll continue along those edges and you'll repeat the same algorithm again. Repeat the same process. So we're going to repeat recursively, and now we're going to treat W as the new root instead of V. Right, so with W replacing the role of V, and then continue, right? And so then you may travel along some, right? So maybe this is, let's say this is W, and let's say in step 2 we stopped at U. Well, maybe W has some other edges that go off into the graph, and so once you stop, you go back to W, and then you treat W as your new starting point, and you continue along edges that haven't been visited, and you keep repeating this until finally you exhaust every vertex in the graph. Right, and so this process is usually known as backtracking. Right, because what you're doing is you're traveling along some path of vertices, as many as you can, until you can't anymore without creating a circuit, and then you just backtrack along the path until like you go back to the last vertex, and if you can continue going from that vertex in an alternative path, you take that path and you continue doing this. And so all the new paths that you construct via the backtracking, you just link up with the first path, right? So you sort of successively link these paths together, and eventually, since the graph has only finitely many vertices, it's going to end, and you'll have a tree, right? Because at each step, you've always avoided creating a circuit. So when this ends, it has to be a tree, because the only way it couldn't be a tree is if you created a circuit at some point. But remember, we always choose our edges so that we don't create a circuit. Right, and so what does this look like for a particular example before we talk about how you would actually code this? Right, so just give me a second to copy over a graph that will run this process on. I think it should be, if what I just said a second ago is still not clear, it should be a little bit clearer now if we actually look at an example. This is the sort of algorithm where if you describe it formally, it sounds more complicated than it actually is. Right, and so let's run the process I just described and find a spanning tree for this graph. And so let's begin with A. So I'll fix A as my arbitrary root. Right, and so this is like kind of like a step 0, and so I'll just initialize with A. And then what I'm going to do is just follow along arbitrarily a path until I can't continue anymore in the graph G without returning to one of the vertices I already visited, right? So maybe I go A to C, maybe C to E. I can go from E to F, F to H, H to K, and then, well, K can go to J. And now I'm stuck, because the only way to continue along a path is if I go back from J to K, but then I would be visiting K again, right? So I stop. Right. So otherwise we would have to visit K again. Right. And so now what we're going to do is we're going to backtrack along this path, right? And so I'm going to use now, I guess I'll use the color blue to denote what we do in the next step. Well, if I backtrack from J to K, notice that in the original graph, there's no new edges leaving K that I haven't already considered. And so we don't do anything, right? So then we just backtrack again to H. However, if we hit H again, notice that there's an edge connecting H to I, which I ignored the first time. And so in this step, in the backtracking step, we're going to link H to I, right? And so once we hit I, well, once again, we're stuck, because, right, I can't continue along any path without returning to H. And so once again, we backtrack again, and now we go from backtrack to H, back to F, right? And so now, once we hit F, well, I have a few options for F. I can either go from F to D or F to G. Let's suppose I go from F to G, right? Once I hit G, it is possible now, if you look at the graph, if I move from F to G, I can continue a path from G to H, But I don't want to add that edge because remember that H has already been visited, right? So I'm going to stop at G and now go back to F and again keep backtracking along the graph, right? And so now once I go back from F to E, well, there's an edge connecting E to D, which I'll add. Once again, I could go from D to F, but I don't want to add that edge because that would create a circuit. So this is when I'm going to stop here. And then again, you keep going back and continuing this, right? So there's maybe one more vertex I missed, which is, sorry, one more vertex that I missed, which is the B, which I can reach from C. Right, so again, you begin with you initialize with some A or some arbitrary vertex, which will be the root. You travel along a path until you can't anymore. And then along your main path, you go back one vertex at a time. Each vertex, you try to do the same thing again. And every step of the way, you want to make sure that you don't create any circuits. And that's basically how this works. Right, and so this algorithm has sort of fundamentally a recursive structure because remember that every time, oh, I don't every time you backtrack, you're basically running a version of the algorithm again for a smaller portion of the graph. Right, so let me demonstrate this in a little bit more detail. Right, so let's say this was my root A. Right, so I run this for some amount of time, and I end up say I end up at W, and say I end up, and then I finally end up at U, and it stops here. Well, what you do is you go back to W, and then maybe W is linked to some other portion of the graph which we haven't discussed yet. Well, now I treat W as the new starting root. And I run another version of the algorithm, but just in the region that's been circled. Right. Right, in this circled region. And then this will give me some spanning tree of the subgraph which I've circled, which you can imagine is there, which I then link up to the path from the first step. And then once you've done that for W, you go back and continue repeating the same process. And notice that, well, if you go into this circled region, which you can imagine is another part of the graph, once again, you may be using smaller versions of this algorithm several times, right? Okay, and so this recursive structure is what allows us to code this, and you'll see that actually the pseudocode is very short for this. It's a lot shorter than you would expect it is, like given the examples we've done so far. Right, so let's talk about how you would write the pseudocode for this. Right, and the idea is, well, you want to use the recursive structure that we just talked about to code it. And so the first thing we're going to do is write a visiting function which tells you what to do when you arrive at a particular vertex, right? So if we go back to this example, you're traveling along, visiting each vertex. At each vertex, you're really making a decision, right? You're looking at which edges you could potentially add. You pick one, and then you can continue along, and you kind of keep repeating the same process each time you visit a new vertex. And so that's the role this function is going to play. So for the sake of this writing out the pseudocode, we're going to fix a particular graph G. So G is simple and connected. You can assume that the vertices have been ordered, say V1, V2, up to Vn. Just for the sake of actually writing this out, you would want to assume they have some order. Right, and so we're going to begin by writing this visit function. right? So the name of my function will just be visit, and it will have two inputs, v, which will be a vertex on the graph, and t, which will be the portion of the spanning tree we've already constructed. Right, so v is a vertex on G. T is not a spanning tree, but a tree which is a subgraph of G. Right, so T is a tree. And so this graph T is going to be what we continue building on until we finally produce a spanning tree at the end of the process. Right, and so how does this work? Well, let's say this is our vertex V. There are a few different maybe there are a few different vertices adjacent to V in the graph. And so you want to imagine that we're at the point where we're kind of trying to construct our path arbitrarily, and we reach the vertex V, and this procedure will tell us what to do when we reach V. Well, remember that we just picked one of the vertices which was adjacent to V arbitrarily, and we just decided to go along, add the edge from V to that vertex to our path. And so what we'll do is build this into a for loop. So for each vertex W that's adjacent to V, we're going to do the same thing. Right, so let's say we begin by going from V to W. Well, what did we do? We just added the edge connecting V and W, right? So I want to add, and we also added the vertex W to our tree as well, because we have to include everything, right? So we're going to add W and the edge between V and W to our tree, right? And so then okay, we moved to W, we added this edge to our tree. What do we do then? Well, we just actually repeat the same process, right? So there may be some other vertices that W is connected to. Once again, we're going to pick one and add the edge and continue on. And so what we'll do then is just run the function again, right? And so now I'm going to visit, instead of visiting V, I'll run the function on W. And I've updated the tree because I've added W and the edge to it. So I'll put in the new tree there, and then it just repeats. Right, so it starts at some vertex. There are a few different options. Right, so let me copy this over again. Right, there may be some number of vertices which are adjacent to V. For each of these vertices, we go to that vertex, we add the edge to that vertex and the edge to our tree, and then we run the algorithm again we run the procedure again with now W playing the role of V. And so eventually you're not going to be able to add anything more to your tree. And so you trace back to the right, so you'll continue along past W for some number of steps. Eventually it's going to stop and you're not going to be able to do anything because you've maybe exhausted all the options. So then you'll come back to here. And then at that point, the for loop moves from W to W prime, and you do it again. And eventually it'll stop. And then you go back, and then the for loop moves from W to W prime, and you do it again, and so on. And then finally, after some time, you'll exhaust all the options, and then you'll be done. Notice that kind of like hidden in the background is that I'm actually, right, each time I do that, I may be running visit several other times, right? I may be running this function many other times, sort of hidden in these steps. And so this is kind of the nature of the algorithm. Great. Okay, and so that's how this visiting function works. We're not done writing the whole algorithm. So now how does the main body of the algorithm work? Well, we'll just write a different procedure, which will use the visit function. And so this is really just to initialize so that it's not like a vacuous thing. And so I'll call this DFS for depth first search. And once again, it's going to have the graph G as its input, right? So the graph G from above. And so what do? I begin by defining my tree T to just be the tree that only contains the first vertex as the root. Right, so this is my starting point. And then what do? Well, I just initialize the visit function at v1. So I run visit with vertex v1 and T is my tree. And then I continue on. And so this is it. Right, and so once this visit function is done, it will output whatever the tree is. I guess maybe you could write in the pseudocode for a visit function that once the for loop ends, you just output T, right? So maybe I should put this up here. Or output or return T, right? And so I think it's kind of surprising how compact the actual pseudocode is for this. I mean, the reason it's so short to write out is because of you're really just doing the same thing over and over again, and you can write that quickly by doing this kind of recursive structure in the for loop. Of course, if you actually program this is not sufficient for writing out a real program, but this is what the structure of your program will look like, right? And so in general, if you have a more complicated programming problem or algorithm that you're working on, you should always try to first by hand write out a sketch of how the procedure works, write out a sketch of the pseudocode before you try to actually program in detail. Otherwise, you're going to get the programming details messed up with like the structure of the algorithm, and it'll make it more complicated if you don't have a plan for yourself to begin with. Okay, and so we wrote out the pseudocode for this. One thing that's worth also talking about is the complexity. Of the depth first search algorithm. Well, so notice that when you're understanding complexity, it first helps to think about like what is the worst possible scenario, right? I'm supposing that G has n vertices, and we want to understand how many steps this algorithm takes as a function of n if G has n vertices, maybe in the worst case scenario, right? So well, let's go back to the example we looked at before with this graph. Notice what we did is, well, we ran along some collection of the edges to produce the first path, which is written out in black. And then we maybe had to go backwards through these edges. And well, for each edge, we only travel through it at most twice, right? Once the first time we go through the edge, and then once when we go backwards. Right, and so you may have to do this backtracking for every single edge. But if you do the backtracking for every single edge, then you're visiting each edge twice. And so in the worst case scenario, your computer will have to look at each edge and do some kind of comparison or calculation 2 times, right? And so in worst case scenario, the algorithm visits each edge twice. Right, and so this means that the number of steps is always going to be less than or equal to, say, twice the number of edges, right? Well, since G is simple, there's no loops in particular, and it's not a multigraph. So there are at most, well, how many edges can there be in a simple graph? In the worst case, it's a complete graph, meaning there's an edge between every pair of vertices. So that's n choose 2. Right? So this tells us that the number of steps is always less than or equal to 2 times n choose 2. Well, what is n choose 2? You can do a calculation that shows that this is equal to n times n minus 1 over 2. And so the number of steps, now it's easy to see that this is big O of n squared, right? So this is a polynomial time algorithm in the number of vertices. It takes about n squared steps, if in general, to find a spanning tree. Okay, and so that's a summary of how the depth first search algorithm works. As with a lot of other algorithms we've introduced in this class, I would recommend going back and looking at, draw like a graph for yourself, which has maybe 10 vertices or something like that, and try to do the algorithm by hand to understand like why, like one, how it works, and two, why is it written in this way. The best thing to try to think about is how the recursive structure works. Okay, and so the next algorithm we're going to look at is very similar, although I think maybe a little bit easier to understand than depth first. So this is called, instead of depth first, it's going to be called breadth first, for reasons which maybe will become clearer in a minute. Right, and so this is another algorithm that will solve the same problem. Right, so you may ask, well, we already saw one algorithm that solved the spanning tree problem. Why do we need another? Well, I mean, it's going to use different techniques, and it turns out that the techniques used for depth first search are useful for some other problems, while the techniques used for the breadth first search algorithm are useful for a different set of problems. So it helps to understand both of them for other applications. And so what I'm going to do is just, instead of listing out kind of how it works, I'll begin the next lecture by doing that. I'll just do an example of this, and then we'll analyze the algorithm in more detail next time. Right, so let me just do a quick example. Right, so just give me a second to copy over graph. Right, so this is going to be my graph G. Right, and so what I'm going to do is try to find a spanning tree of this graph in a different way. And so what I'm going to do is I'm going to choose, this is going to work by picking different stages, different levels of vertices. And so level 0 will just be some point which you initialize as the root of your tree. And so, well, let me just pick A as level 0. And so notice if I look at A, well, it's connected to B and C. And so I can add these edges, the edge connecting A to B and the edge connecting A to C, without creating a circuit. So I'm going to do that at level 1. I'm going to add B and C, and the edges connecting A to B and A to C. Right, and so that's my level 1. Well, level 2, I'm going to repeat the same procedure now, except I'm going to look at B and C individually. And let's say I look at them in this order, right? So notice that I can connect B to G and also B to D. So I'm going to add G and D. I'm going to copy this picture over up here so I have more room to draw the tree. So remember, at level 0 we had A, level 1 we had C and B. Right, so let me use black for level 0 and 1, and let me use, say, blue for level 2. Well, I'm going to add the edge between B and G, and also there was an edge between B and D. Right, and so those are all the options I can add to B, all the other new vertices that B is connected to. And so now I move on to C, right? I move on to the next vertex that was chosen in level 1. Well, it is true that C is connected to other vertices, but the only vertex that C is connected to is D, which we've already added to our tree. And so I'm not going to do anything, right? Because if I added an edge here, I would have produced a circuit, but I don't want to produce a circuit, so I'm not going to do anything with that. Right, and now hopefully at this point you can see how this is going to work, right? So now I move on to level 3, and now I apply the same procedure for G and D. Starting, let's say I do this alphabetically, right? So you always have to have some order. So let's do D first and then G. Well, D is connected to well, notice that D is connected to G, but I don't want to add that edge to my tree because then that would produce a circuit between B, G, and D. However, I can add H to my graph, right? So D is connected to H. So let me use red for level 3. And so there's this link between D and H. D is also connected to B, but I've already included that edge, so I don't want to do anything. And so we're done with D. So we're not done analyzing everything in level 2, right? I want to also move on to G. I haven't looked at G yet. Well, G is connected to several vertices, including in particular 2, which we haven't included so far. For example, G is connected to E, so I can add this edge, and also to I, so I can add this edge. Right, so I'm adding H, I, and E to level 3. And then finally at level 4, you're going to do the same procedure. Maybe you want to reorder this so that it's alphabetical. You can see though from our picture, there's only one more edge to add. So we're going to add finally F at level 4. F is connected to E. Right, so maybe I'll use green for this. Right, and so this is, now we're finally done, and so we've produced a spanning tree. Right, and so for the next lecture, we'll begin by returning to this example and then talking about how the algorithm works in general, writing out the pseudocode and looking at the complexity. It turns out that the complexity of this algorithm is the same as the previous one we looked at, so it's also going to be big O of n squared. But it helps to know how both of them work for reasons I mentioned before.